Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture. This is on design analysis of gear pumps and this is part 1. Now, external tooth gear pumps with involute or similar teeth are widely used in fluid power application. Gear motors are not very common, although there are some models of gear motors, but this is not very common with involute teeth. Gear motors with different teeth such as orbit motor is very popular. However, the involute tooth gear motor is not that popular because it is not much beneficial to use such units for motor. Now, units with external gears are called as external gear pumps and motors, and units with internal gears are called as internal gear pumps or motors, or the together either it might be pumps and motors because they basically features will be same, they will look alike, only there is a minor change in valves. They are usually called hydrostatic units. So, you may call external gear hydrostatic units or internal gear hydrostatic units. Although gear type hydrostatic pumps enjoy a high level of reliability and offer a low purchase cost to the end customer, they are often with performance characteristics that tend to create higher noise levels than other types of positive displacement units. These noise levels are associated with the substantial flow ripples of the unit, which induces a pressure ripple and oscillating force within the system. Since the flow ripple in case of pump is considered to be the first cause of these oscillation forces, it is assumed that a smoother flow delivery of the pump will also attenuate the noise that is generated. In this lecture, the working principle, flow ripple and reliable characteristics of an involute gear pump are discussed. Now, first of all, what is the working principle of gear pump? While considering the operation of a external gear pump, it is common mistake to assume that the fluid flow occurs through the center of the pump where teeth of meshing gears comes in contact. Normally, if a gear pump, this plan view is seen, then many people may think that as the gears are rotating in this directions, so this must be flow in and this must be flow out, but actually it is not. It is otherwise. If you look into this picture, that is, in that case you can see that it is rotating in the clockwise directions. Let us assume the blue one is the driving one. Among these two, one of them is driving one. In this case, let us consider this blue one is the driving one. Then what we observe, the oil is coming in from this side and then it is being trapped and it is going out. Okay. and if you look into this view, the soil is coming in like this and oil is going out like this. So, this should be, this is the direction of the flow. So, in fact, again what we think that okay, direction of flow we have corrected. Now, how it is the oil is being pumped out, and we should remember that input side pump is usually atmospheric pressure, whether in the output side pressure is high, this is the working pressure, and as earlier we have learned, it might be in the range of 10-15 megapascal in case of gear pump, may not be as high as in case of piston pumps, that is cylindrical piston pumps, where it can be attained up to 30-40 megapascal, but here the 10 to 15 megapascal are very common. Now, then again how it is being pumped, because we need a lot of pressure to generate. Now, again to looking into this figure, one may be confused with this wheel pump, bucket wheel pump. You might have seen in the paddy field, usually you will find a wheel with bucket fitted on the periphery, that is used to fetch water from the pond or water source to the ground. Usually ground level is slightly higher than the water level, and in that case what is done, it is as if the scooping the water and then it is put into the ground. Now, that is something like a bucket elevator, there the water is taken into the cavity of the bucket, captured into the bucket, and that is taken out. If we think of the pressure is almost same. Now, in this case it is not that, the fluid is being taken by this pocket and it is going simply out. There is the suction and compression action by these gears. Now, to learn that, we must find out that where is the suction and compression chamber in that. To produce a flow, we should say, with a gear pump, fluid is carried along the periphery of each gear within pockets between two consecutive teeth enclosed by the casing wall from the intake side to the discharge side of the pump. Now, in that case, if we asked what is the, how many chambers are there, we can say that within one revolutions there are how many pockets? This is exactly the double of the number of gear teeth. So, one may consider that is the number of chambers in a gear pump. So, number of chambers are high, and as we have learned earlier that with the increased number of chambers, actually ripple reduces. Then at the first statement I have told that there will be high ripple. That is due to the fact that here this compression and geometry of the volume discharge is such that we have very high peak of the ripples. So, it is like that within one revolutions, if there are say 10 teeth, so 20 chambers. So, there will be, but there will be actually 10 ripples, because two pockets are giving the flow together, and you will find that ripple is not same as in case of the piston cylinder. So, there is difference. We will show that curve later of this lecture. Now, on the inlet side, the gear teeth are coming out of the mesh and thereby creating an expanding space among the two contacts at casing and the driving and driven gears. Say here, if we consider this contact point, that is separating the high pressure zone to low pressure zone, and from this point to this point we will find when the gears are moving, this space is increasing. So, there is a suction, whereas in the other side the space is, that area is decreasing. That we will derive, that how much area is decreasing or increasing, that has to derive to find out the flow rate of such a gear pump. Now, it creates a suction zone, the inlet side it creates a suction zone. Then in the an intake volume is then trapped into two pockets. Here is one pocket, here is another pocket of two gears and carried to the delivery or outlet side. And in the outlet side, gear teeth are coming into contact and thereby creating a contracting space. Thereby fluid is squeezed out through the delivery or outlet port. So, this is the pumping action in case of the gear pump. And in case of motor, if we think of the motor, then this process is just reverse. What will be in that case? The oil will be pumped in from this side, okay, in case of motor, and volume will expand. So, this will be then high pressure side and this will rotate in the same manner, whereas the low pressure oil will go out, but it will transmit that this pressure will be converted into the force and torque, and that can be taken out either from both the gears or from a single gear. Okay. It can be shown that the volume displaced among three contact, this is the three contacts, one contact is here, another contact is here, and another contact is here, and then two contacts of two gears with casing and meshing teeth at centers at both inlet and outlet. So, one chamber means just consider the instantaneous, the last teeth in contact with that, this side and this side, and the contact point here. So, this is the compression chamber, and similarly the suction chamber is with this contact point here and the first contact point coming to the wall, and this side the first contact coming to the wall. Okay. Exactly equal to the summation of active amount of trapped volumes between two consecutive teeth of gear of each gears. This means that what is the total expansion or the compression, that volume, this volume will be exactly equal to this two pocket volume. But here is one confusing statement is there. If we just measure this area one pocket and here one pocket, this will be same, and if we multiply them, then that would give the total volume, but it is not that. It will be these two volumes minus this entrapped volume, which is actually inactive. If you stop this gear, you will find there is one small volume, the same oil is coming back to the suction side, that we have to subtract, that we should remember. So, while we are calculating this, we have to consider this part. However, if we calculate the total displacement of this area during the suction and compression, then automatically that will be deducted from the calculated area. We need not bother about that, how much pocket. That means, if we give more undercut to these gears, that will not matter, that root fillet. If we increase the root fillet, that will not really matter. This is one thing. Second thing which I am going to show now, that one important factor is that actually each and every when it is passing through, there will be some oil leakage through the even through the contacts, that we should take care of. In that way, efficiency of this gear pump is lower than what is available with the cylindrical pump and pistons. Another part which I would like to describe here, which I would like to discuss, that is, if we consider in case of pump, here the pressure is low, maybe the atmospheric pressure, whereas here the pressure is high pressure. Now, if we consider the pressure curve here, you can see this pressure is not increasing, not increasing, not increasing, and then when it is being exposed, suddenly the pressure is increasing, if it is in case of ideal case. But what actually happening, that there is a small amount of leakages. So, what we will find, whatever pressure here, maybe some pressure is increasing, and then suddenly it is being exposed to high pressure. Now, that causes some sort of the fluid borne noise. To reduce that, as well as to balance this imbalance in the torque, what is done, that this somewhere a pocket is made here, and that is connected at the midpoint, and then again another pocket is made here, and then it is connected here, and then ultimately pressure distribution is comes something like this. This is high pressure, and gradually it is decreasing. That sort of pressure distribution will be better for the performance, and that is done by such grooving. However, we shall not discuss anything about such grooving, because for that we need some more complicated analysis. But anyway, I will show you the flow between these two teeth. Now, look at this figure. As you can see, you see just how the flow is taking place. In that case, see, this is rotating in the clockwise, and this is, so this must be, which side is the delivery side, this side or this side? So, this side is the delivery side. As we look into this delivery side, not much this flow phenomena is being looked in, but what we find, as if there is a flow is taking place in this side. Say, look at this, at that moment what you find, that fluid is sudden fluid is going out. That is a leakage. That leakage is very important, and in designing such gear pump, controlling such leakage or correct estimating of such leakage for the analysis of gear pump is very important. Okay. Now, of course, within the scope of this lecture, we cannot analyze such thing. Only what we will analyze between this contact, say this is, look at this contact, this is the separating chambers. Now, this point is separating the chambers. Now, this point is separating the chambers. So, something is happening there. Analysis of this will be very important. Now, we shall try to find out what is the volume displacement. What we would do, if we can calculate the variation of this area with shaft rotation or with respect to time, then we can multiply the width of this gear. In case of piston pump, what we do, we multiply with a constant area with the variable stroke length. That length is varying, but the area remains constant. In case of this pump, this gear pump, what we find, that area is varying and the width remain constant. So, if we can't analyze the variation of area with the shaft rotations, we can easily find out the volume displacement, and then considering the time rate we can find out the flow rate, theoretical flow rate. Now, before going into the analysis, we have non-dimensionalized the variables. That is important, that we should understand how we have non-dimensionalized. Okay. Now, what is the benefit of that? To know that in order to interpret results obtained for any physical size of palm, it is conducive to non-dimensionalize the various variables. This means that if we know the shape, geometric shape of the teeth, number of teeth, few parameters should be remain same, remain constant. Then what we can do, irrespective of the size, we can go for analysis. Then whatever result is available in non-dimensional form, that we can simply multiply with the real size, some size with respect to we have non-dimensionalized, then we can get the actual size of this pump. Say for example, we have taken a pump of the gear 10 teeth for the driving and 10 teeth for the driven. Then maybe module is 5, say. Then whatever flow we are getting, if we reduce this module to 1, definitely flow rate will be less. It may be 5 times less, or maybe something else that can be found out from the non-dimensional parameters. But once we design this pump with a particular module, particular teeth number, we can find out what will be the real output, input, etc. Now, how it is non-dimensional, that we shall examine now. Before that, furthermore, this will also simplify the development of equations by eliminating various scale factors within each equations. Hence, the final results may be simply scaled according to the rules that were used to non-dimensionalize the specific quantity of interest. The dimensionless variable used in the analysis are given as follows. We will see this. Now, here for linear parameter, we have considered the reference parameter as the base circle radius of driving gear. Perhaps you know that once the gears, say involute gears, we say that this is the module, this is the teeth number, then and this is the pressure angle, of course, pressure angle should be there. Then one dimension of that gear will be fixed. That is, normally we make a mistake, perhaps the pitch circle is the fixed dimension, but it is not. The fixed dimension will be the base circle, that on which the involute is generated. Okay. Now, if you introduce the correction, correction means it might be the profile is shifted. In that case, we will may have different pitch circle radius, even with uncorrected gears. If they mesh with a enlarged expanded center distance, we will have a new pitch circle radius, but the base circle radius will remain constant. That is why this parameter is taken as the reference parameter for non-dimensionalizing. Now, another information is there, that we have used a caret to denote the dimensionless quantities. So, in that way, now L, it is actually instantaneous length of action of the gear in mesh. I will explain this again with a figure of the gears, and non-dimensional means with this caret or hat you can say. So, L divided by RB1 is the non-dimensional parameter. Similarly, R is an arbitrary radial dimensions. This is also divided by the same base circles. In that way, any in the Cartesian coordinate x, y coordinates are also non-dimensionalized, and the rho that a radial dimensions, it is not arbitrary. We can say this is from the contact point, actually radius from the contact point. This is purely arbitrary, and this or general radius, and this is the specific radius with respect to the point of contact. Okay. Now, this is the linear dimension, we have non-dimensional in this way, but there are some other dimensions also, for example, the volume etc. In that case, what we consider the width, we consider the real width of that machines, or the width in the parameter we consider divide the volume by width and then also speed. Then now, this volume is bulk discharge volume, this is divided by the width W, that means what the non-dimensional volume, that is per width, unit width, and then area is divided by simply by RB1 square. So, this volume is non-dimensionalized. Now, we can non-dimensionalize this volume by this, we dividing by a volume width into RB1 square, but again flow rate. So, we have to introduce what where we have introduced that omega 1, what is the angular speed of this, or in other words, if we carry out analysis with non-dimensional parameters, then if we find some volume, non-dimensional volume, simply we will multiply the actual real parameter of the gear pump which we have considered. We shall consider that width, we shall consider that RB1, that base circle radius, and in that, in case of flow rate, we will consider the actual speed. But here one thing I must mention, that this gear, two gears, mostly you will find they are with same number of teeth. That means, if this side is 20, other side is also 20, but it is also possible that one is 20, other is 18, other may be 16, this is also possible. In that case, if we non-dimensionalize all this diameter with one base circle, in that case base circle will be different base circle, then we have to take care while we are considering the some real parameters. But it is possible, because knowing the number of teeth, we know the base circle of other one will be the simply the ratio of this gear teeth. So, that is not, will not be difficult. This is in case of external tooth gears. In case of internal tooth gears, as you know, that numbers will be different, because if the ring gear is of say 20 teeth, then external tooth, internal gears of that one has to be at least maybe 4, 5, 6 less than that. So, in that case, you can make the parameters non-dimensional considering any one base circle radius, but while you are converting the real data, you have to consider the other base circle also with proper proportion. That is not difficult, but one should take care of that. Okay. Now, so we will now go for this analysis. In that case, as you see that these gears are rotating like this, and this is flow in and this is flow out. Now, here what we have written, this is, say, look at these dimensions R A 1, this is the tip circle radius which is called also addendum circle radius. So, R A 1, in that case we have considered this R A 2, this is gear 1, and as well we have considered this is the driving gear and this is gear 2, this is the driven gear. We have shown the same number of teeth here. So, these dimensions will be same, but we will, while we are analyzing this, we will consider that these are different. And then the theta 1 is the angle of rotation of this one, and omega 1 is the speed of these gears, and these two volume I shall discuss during the analysis. However, this rho 1 is the distance between the contact point to the center, and you should remember this rho 1 and rho 2 is varying as the gear rotates, because this contact point is along the line of action, and it is therefore, when it is contact point moving from one side to other side, then definitely this rho 1 and rho 2 are varying. Now, we have made some assumptions. These are: the fluid is incompressible, because to consider the change in area, we have to, if we consider the compressible, then we have to consider that not only due to this area change, but also due to the compression the volume may change, I mean the total quantity of the fluid may change. So, if we consider incompressible, then we need not bother about that. Fluids leakage are negligibly small and neglected. Also, components of the pump are rigid and inflexible, that we have to consider, although the in some analysis this pipe is considered that flexible, that will complicate this analysis. Now, the important thing is that to analyze this, as I told, that these 3 points will constitute the chamber. Now, when this point is moving in these directions due to this clockwise rotation of that, then this point is moving, but what you find that after a small amount of rotation, then this chamber will be connected, because this path will be open. Then immediately at that instant we have to consider this contact point and this point. So, this we have to be careful, or we should take care while we are considering such area, that there should not be change in certain opening of this area with when this one pair is contact. Maybe when the second pair is coming in contact, then again the same phenomena is there. If within this contact zone, if one teeth come, I mean the open passage is opened, then analysis will be complicated. That also we have considered. That means when one contact, one pair is contact is there, then same teeth is here, only this point is moving on the wall. Okay. Now, if we consider the hatched area, so that area, if we can calculate that area including gears, gear that means the metal part and then fluid part, if we consider the variation of this area with respect to this contact point, that definitely will give us the variation of area during the rotation, and from there we can find out the expansion and compression. At a particular instant of time, the boundaries of this chamber define the control volume. We consider this as the control volume. Since the fluid is incompressible, the total volume entering the discharge chamber must equal the total volume leaving the discharge chamber, that constitute the control volume. Then we consider dVd is the flow out, and we for the analysis we consider a very small amount of that is crossing the boundaries of the control volume at a particular instant of time. The material within these volumes is irrelevant, since everything is considered to be incompressible. Okay. However, the infinitely small volumes generally consist of both gear pump material like steel and fluid. In this case, we have considered steel, it might be something else also. So, but the thing is that one is that material, solid material, and another is the fluid material. The input volume to the control volume from the driving gear, that is gear 1, is denoted by dVi1. So, when this is very small amount, say d theta 1 rotating, what we find the dVi1 is going inside this control volume. That means, within this boundary what we have considered. This boundary itself is varying, but we have to consider in terms of flow in and flow out, the volume in and volume out. A certain amount of gear volume is also leaving the control volume. This existing volume, exiting volume from gear 1 is denoted by dV01, whatever volume is going out. Okay. Similarly, the entering and exiting volumes from gear 2 are represented by dVi2 and dVo2. Okay. Since the input volume is equal to the discharge volume, the dimensionless governing equation for this problem will be, so dVd, here we have considered non-dimensional parameters. So, input minus output, and here also input minus output. So, total this volume, whatever this volume will be there, that must be going out. If there is no difference, there will be no volume output. In fact, in case of, if we consider simply the bucket type of pump, bucket wheel type of pump, then this will be 0, both will be 0. There is no such expansion and compression in the control volume, but in this case it will be, we will find out that. Where this input we can take, if you look into this figure, half RAI into RAI sin d theta 1. So, sin part of this one, d theta 1 is the volume, into W, that will be the volume displacement. If we consider this infinitely small amount of shaft rotation, so sin theta part will be something like this here, that part into this length which is RAI into half of that. We have considered the area of triangle and then multiplied with the width of this gear W. This is simply volume area of isosceles triangle and width. Considering angular rotation to be very small, now we can assume sin d theta 1 is equal to d theta 1, and in that case we can express the dV I1 is equal to this much. Now, if we non-dimensionalize this volume, then we will get dV I1 is equal to half into RAI hat square into d theta 1. Similarly, we have also the relations found out in the same way. You can look into the equations, these are same. In that case, when we are calculating the volume out, we have considered this radius, because this is the radius here. We have to consider a small amount of rotation, and then this triangle formed by two arm is equal to rho 1, in this case rho 2. So, this will be the equations. Now, we can rewrite these equations. Here subscript 1 and 2 denotes that gear 1 and 2, we need not mention, already we have mentioned it. and R A is equal to the addendum tip circle, rho is the instantaneous contact radius, theta is the angle of rotations that we have already mentioned. And then from the fundamental law of gear, now we have written these 4 equations. We will, before substituting these into the main equation, we shall now from the fundamental law of gears, we know again this relation is that d theta 2 is equal to r p I by r p 2 d theta 1, and where r p indicates the pitch radius. Substituting equation 3, 4, 5 into equation 1, we get these relations. Okay. So, remember the first equations and then all the equations we have derived so far, we will arrive into these equations. Now, in this derivation, they have considered the pitch circle, but I prefer normally, or anyone can prefer just directly the base circle. You can consider the base circle instead of the pitch circle. But considering the pitch circle is that when on this this point will come on the axis, on the line joining the two centers, then this rho 1 rho 2 will be equal to the r p I and r p 2. Remember that fact. So, maybe this will be better to use at this moment, but anyway this will give the same relations. Now, introducing theta 1 is equal to T W 1 time into omega 1, and that at theta 1 is equal to non-dimensional. So, we can consider that this itself is dimensionless time, the angle itself is the dimensionless time. This is a tricky things, but one can consider in this way, because d theta 1 will give you d t 1, rate of change of time if any there. So, this expression you have to visualize this. Now, we have that means non-dimensional time is equal to simply the angle of rotations. The final equations of the theoretical flow rate of the gear pump in dimensionless form is obtained as. So, now what to find out the flow rate, what we do, we differentiate this volume with respect to the time, and then we will find this final relation will be in this form. Okay. Then now, in this equation what we find at any instant, say this is a fixed dimension, fixed parameter, this is also a fixed parameter. Once the gear we know the center distance, these two are also fixed parameter. Only with time this rho 1 and rho 2 are varying. So, we have to calculate now these two parameters. Once we can calculate, we can easily calculate this one, the volume displacement. To determine the instantaneous flow rate of pump, the instantaneous length of action is to be found out from mesh geometry. That means, if you go back to this figure, that we will find, we have to find out the instantaneous length of contacts, means from the pitch point to the actual point of contact, that length we must know. Also, we have to find out rho 1 and rho 2, and then it will become very easy to estimate this flow rate. Now, we consider this geometry of these gears. In these gears, say this is the driving gear, we have considered also the contacts points. Now, what we find that first of all we must consider the coordinate system to analyze the gears. In that case, what we have considered that the midpoint of the teeth will be on this axis when theta is equal to 0. no, not midpoint, sorry, I have made a mistake. This is the pitch point, but we have considered that when one teeth is coming in contact, first contact, that is that theta is equal to 0. Now, we have shown that here the first point of contact, and then we have also shown some intermediate point of contact. Okay. Now, what else are shown here, that from the midpoint of a teeth, so this is the angle zeta, and beta 1 is angle from that line to the point of contact, instantaneous point of contact, and then theta 1 is the angle of rotations. Okay. These we have considered, and we have considered two axis system which I am explaining. In coordinate system and mesh geometry, x and y, capital X and y, the fixed Cartesian coordinate system, that is the fixed reference, and this angle, and it is oriented by a theta angle with the line joining the center of gears. Okay. That means, what we have considered, that when this first contact point is there, we have taken the axis through the midpoint of this one, which is oriented at this angle, and this coordinate system capital X and capital Y is a fixed coordinate, and then we have considered the another x y coordinates. However, this will be determined later, we will show that how it can be determined, and x y is in the rotating coordinate system which is fixed to the driving gears. This x and y, that coordinate is fixed to the driving gear. Now, theta is equal to 0, theta 1 is equal to 0 when these two coordinates are coinciding, that we have to remember. It is so chosen that while the tooth mesh begins, this x coordinate passes through the midline of the driving left gear tooth in contact. Okay. The rotation x y defined by theta 1. Theta 1 is the angle of rotation of the driving gear. At theta 1 equals to 0, x axis coincide with the capital X axis, small x axis, that way I have already explained. Now, using the law of cosine and the geometry with reference to figure 4b, which means that we have considered the intermediate point of contact, some point of contact, it can be shown that the instantaneous radii of tooth contact between two meshing gear is given by this rho 1 is equal to L square plus R P 1 minus 2 R P I L sin alpha. Now, this derivation is shown here. You can see this, you can write down this square must be equal to R P I minus L sin alpha square plus L cos alpha square. Now, if we simplify this, we will arrive into this form, which we have non-dimensionalized and used in this equation. This is not difficult to find out. Similarly, rho 2 square will be expressed as like this, but remember this sign. While alpha, where alpha is the pressure angle and L is the instantaneous length of action from pitch point P to the current point of contact. That means, this is the pitch point and this current contact is defined by L. Now, if we substitute 8 and 9 into equation 7, we will get this equation in this form. here comes this L square. Okay. So, the instantaneous point of tooth contact, which always lies on the line of action, can be defined in polar coordinates by radius rho 1 and theta 1 with respect to x and y. Now, the equation of line of action with respect to x y coordinates system is expressed as y dash sin alpha minus theta 1, the angle of rotation, minus this. If you just look into this geometry, and you will arrive into these equations, is equal to 1 minus x dash cos alpha plus theta 1 minus zeta. This is the equation of this line of actions. Then from the gear geometry, the base circle radius RB1 is equal to RP1 into cos alpha, that is known. Now, keep in mind that alpha, in this case what alpha we have considered, that is the working pressure angle, not the actual pressure angle or the standard pressure angle, that you have to remember. This means that while you are going for this analysis, you have to know that what center distance they have made and the gear correction if they are produced, and from there we have to find out the actual working pressure angle that we can put. But in normally in case of this gear pumps, we do not change the center distance. So, even if the corrections are introduced there, the alpha remain constant, that is remain standard one. The instantaneous tooth contact point x is given by this, y is given by this is simple. Then we substitute this in equation 11 and rearranging the contact point is defined by this equation. Now, again from the geometry of involute tooth profile, beta 1 is defined as, beta 1 is this angle. This can be defined as by this. How? We will see in the next slide, but we should look into this psi 1 angle is pi divided by twice z1. Okay. Pi divided by twice z1 means we have taken this angle, not this angle, this psi 1 is somewhere, it is not shown in this figure, but this is pi by twice z1. Pi by z1 is equal to the 1 half the pitch, and this is half of this teeth angle. Perhaps we have to show this one, this angle to be defined, it is given here. Equation 12 and 13, the earlier equation, must be solved numerically for a given theta 1. Okay, these equations you can see that there is no solution, direct solution, we have to solve it numerically. However, this is also analytical solution will be available, we will come into that, but let us see this how this expression how this is derived. Now, referring to this figure, you can see this, now you can see this angle here, this angle is given. So, this angle is this much, this is okay. We have considered this angle, that means this is the half of the teeth, this angle is the half of the teeth angle. Okay. Now, here these angles are defined, and then we can write down this equation, this rho is equal to R B into 1 plus this angle. This is the R B and this is the angle. So, we can define like this. Okay. Now, next beta is equal to, from the geometry you can find out this, and then transforming these into Cartesian coordinates we can write down these equations, and also R B is equal to rho cos gamma and this is equal to, this is from the property of involumetry, we can find out this also, and then after substituting all this equation together, we will arrive to this equation which we have used as a equation 13. Now, next, referring to the starting tooth contact point through this figure, we will now find out the starting tooth contact point. Now, this coordinate again is given by this one. If you look into this geometry, we can have this equation. Now, here S indicates the starting point, this rho 1 at starting, that is denoted by rho 1 S. As well, L S is the length of instantaneous contact point at starting, and the starting length L S is expressed in this form from the geometry, and then from equation 15 and 13, angle zeta, angle xi now can be derived with respect to the starting contact point parameters, and this angle is equal to, is expressed by these equations. So, now we can derive what is this angle. If we know this angle of contacts, this we can calculate this angle also, where this rho 1 S is equal to rho 1, which already I have defined. Now, instantaneous length of actions, again looking into this figure, what we find, sine of this angle is equal to, given by, this is of course in the dimensionless form. So, this we can find also, this L length we can find out from these equations, which we have rearranged, and once we can calculate this, we can find out this also. But still remember, these relations are nonlinear, hence numerical solution to these equations will yield the most accurate results for instantaneous length of action. Okay. However, a closed form approximation to the solution is proposed by the Small ring. This you will find in the reference which will be discussed in the next lectures. Now, I would like to say this, all such analysis were not available till dates, although the gear pump may be of being used from the 1950s or so, but this analysis only recently this analysis was done, which really showing how this area can be calculated. Anyway, we will discuss this in the next lecture. This paper is important. If you have time, then you can go through this paper. Unfortunately, this year is not given, but I think it is in the 2004 or maybe 2005 only. This was this research work was done. However, we will discuss also there is another method to find out such volume in the next lecture, and what we find that you can also go through these papers if you have interested, if you want to learn more about this. But if you read this and these two papers, you will mostly understand what I am trying to tell you and how to find out this volume displacement. Okay, this will be continued in the next lecture, and I thank you very much for listening.